Thank you very much. Actually, I gave two titles in my communications. So one was temporal structures of social processes, and one was about structural social processes. But something that's the kind of ballpark where of what I will talk about. So in the beginning, I had a very great ideas of kind of taking all the kind of thoughts about like time and temporal structure and how that relates to like the society, and to connect them all together into a grandiose theory that leads up to my work. But as you can already guess, that the ambition didn't really become true. So what I will do instead is to kind of take some kind of snapshots here and there of what people have been interested in and how people have been thinking about time and structure in time and networks. Okay, so but before I get to that, I just wanted to kind of share my own journey. So I'm trained as a physicist, and why would this be interested in the social structure of time or temporal structure of society? Well, I mean, when I started out as a PhD student, the picture to the left here is a typical like textbook picture from a course in statistical physics. It shows the Ising model of a magnet. And at that time, I really enjoyed this very kind of abstract problem solving that is related to the Ising model. But I didn't like the fact that I couldn't talk to anyone around me about it. They were just not interested in magnets, you know. But around this time, I came in contact with a sociologist who is Fredrik Liljeroos, was a student of Peter Hellström, that I think all of you know, maybe many of you know Fredrik as well. So he introduced me to Thomas Schelling's models of segregation, and you can just see the visually similarity, like abstract stuff on a lattice. And wow, I realized there's a chance for me there to do something that's both interesting and kind of fun to think about. So ever since then, I've been interested in this kind of interface between mathematical modeling and networks and computational stuff and society as well. And yeah, I've been around in the world pretty much, as you can see by this timeline of my career. Also in the science, I've been going from different disciplines. So I'm a restless soul, I guess. But okay, so let's kind of get started on the real topic. And I just first want to start with a dictionary definition of time. And like it's a favorite topic of philosophers. Like basically every single philosopher had some thought about it. And well, okay, so a typical kind of textbook example. This is actually from Wikipedia, but you would find something in more kind of noble sources. But I like this one from Wikipedia actually. Time is a continued sequence of existence and events that occurs in an apparently irreversible succession from the past through the present and into the future. What I think is a bit interesting here is that there is an apparent irreversibility in time. But if you think about, people doesn't have a big problem to imagine that time is reversible and that you can't kind of time travel. I mean, there are lots of stories about that. And people can imagine that the time is cyclic. There are several religions that believe time is cyclic. So kind of, as opposed to the kind of spatial dimensions, that I think people are much more flexible to think about time. And maybe there is some kind of deep truth hidden in there. But of course, like physics, and me being a physicist in some sense, has kind of claimed this concept more than other disciplines. And in physics, actually, I mean, the kind of linear time of the Newtonian mechanics, it is very successful and works almost always. But if you go to kind of very small scales and the very largest scales, it breaks down. But then again, so this is a quote from the popular science author Carlo Rovelli, that none of the pieces that time has lost, I mean, lost through the advancement of physics, including singularity, cosmology. There is no kind of singular starting point of the universe. Direction, independence, the present, continuity, puts into question the fact that the world is a network of events. So this is something I like a lot, because like temporal networks, the kind of core research theme that I had for 15 years or so, which I will talk about later, it's really about networks of events. But okay, I will leave the fluffiest part of the philosophy now, and well, maybe not actually, because I also want to say that a lot of what I will talk about today, I think from a kind of idea point of view, it relates to structuralism in social science, and that's something I think you've been reading about. This bearded gentleman represents structuralism here, but I think, yeah, like all like the big kind of ideas that have been flowing around structuralism kind of comes alive in network science. The big difference, there are differences though between this kind of mainstream social science structuralism and network science. Like the usually in social science, structuralism means that you talk about some kind of unobservable thing that is kind of underneath everything else. But in network science and computational social science, it's more about what you can actually measure. But there were early research, right? So I just want to kind of highlight this. I'm sure many of you know about Helen Jennings and Jacob Marino that were so much ahead of time, measuring social networks in the 1930s, and introducing both these kind of ideas of structure as I speak of it now, not as the Levi-Strauss and de Saussure and so on, but the structure as like something we can observe and how it differs from randomness. So I think the first three, I mean, this using structure as something, how the observed differs from the random, and using random graph null models to do that. So point 1 to 3 there was from this paper that I wrote, which is one of the later papers. And the degree distribution, I think, is Helen Jennings as a single author. It's a different reference. But this is kind of like both embodies the ideas of structuralism and also takes it to the kind of present day. So it's almost like they visited from the future. Very cool stuff. But okay, let's go back to the future. Yeah. So this is the how I think of data. Usually, like data as it arrives to me, studying some kind of social system, would kind of, you can measure structure in it, in both in terms of networks, in time and space. You can argue that there should be more categories, but for me, this is the kind of abstraction I have in my mind. And these are some topics of my research. I think I did it sometime when I had to present all of what I'm doing, which is very difficult because I'm interested in too many things. But yeah, so things get extra interesting in this kind of like interfaces of where things overlap. And yeah, so today it's talking about this blue region, which sometimes overlaps with space, for example. And this is where geographers have been very trailblazing. Maybe they should be. It's the kind of their topic. So I just want to give a shout out. I've always been a fan of geographers, and I'm teaching information visualization. And one thing I learned from teaching that is like whenever there is something that is kind of embedded in space or time, then you would be surprised like how early people were to show things. And whenever it's something that is relies on some abstract data, you'll be surprised how late people were to visualize it. But isochronic map shows the distance from one point to another, the travel time, in this case, London. This is from the Francis Galton, the father of eugenics, I think, so a bit dubious, but you can see how long time it took to travel. Or you cannot, because I must have hidden the legend. Okay, here's another. This is much more nice, but it's about Berlin, and who knows what is around Berlin. So I thought I showed the other plot. Okay, anyway, so this is an example of like visualizing time and space together. But we have better examples, and they come from this Swedish folk hero, Torsten Hägerstrand. He was the first, I think, social scientist to use computer simulation in his PhD thesis in the 1950s. And then he focused on the diffusion of innovation that you can see to the right, but he also founded this division of geography called time geography, which and the basic idea in time geography is to represent the time dimension as a spatial dimension, and look at the kind of like structures that you get when things happen in space. So in this example, there's a person moving around in the city she lives in, and whenever you stay put in a location, you're following these tubes. And then typical patterns is that people get together at the same place that would kind of look like a bundle of these timelines or world lines. This is another example from the time geography literature where if you travel from one point to another, and you have to do that within a given time, the opportunities in space kind of form, so in space-time form what they call a prism. So it's a lot of funky ways of thinking about time and space that goes on in the geography literature. So shout out to them. Okay, but yeah, now we're getting closer to really what I'm doing, like which is time and events. I mean, eventually it will be networks, which is like events happening between two people. But this is a more general. This is also from the geography literature. I think this is an extremely elegant visualization of different persons' way to organize their lives. So these shows how people go from different types of activities. So all around this clock, there are different activities. They spend time with the family, and then at work and grocery shopping, whatever, and that all forms this pattern. I've always been thinking about picking this up and do some modern remix of this, but no time for that yet. The sociology also knows how to study time. This I think is pretty cool. It studies the waiting time and how that depends on is related to social class. Essentially, the more affluent people, they wait less and they are less patient. So, and back to the kind of computational social science. This is from my colleague Talea Aledavud and Sune Lehmann, Jari Sarmäki. It studies from a network of a data set of cell phones. This famous Copenhagen network study, like when people are active and like following their routine. So in this top left figure is the kind of deviation from the normal. So some people are later in the morning and earlier in the night. And so they define it, they call them owls, the people are awake at night and active at night, and larks, the ones that are active in the morning. And I think it turns out that the owls have a much bigger social network. I guess that what we can see in panel B. And yeah, so those social people are more of night people. I think this is a kind of nice, elegant discovery that you can do from this big passive data sets that we deal with in computational social science. Let's see, I'm just going to go on with this kind of like examples of how people have been thinking about time and structure about time, and then eventually reach my own research. Yeah, so one thing you will hear about in the literature a lot is the relating to time is a waiting time paradox. There's a very related thing called the friendship paradox too, and these are both related to quantities that are sampled in proportion to their value. So you kind of compare, maybe naively, you would compare an average to the second moment. And so that, of course, leads to a bias. Honestly, I feel both of these are not paradoxical at all and very intuitive. So I feel very uncomfortable to call it a paradox, but that's what they do. So the waiting time paradox, it tells you that, I mean, you would always have to wait longer for a bus than the average time between the buses. Because the best scenario is that they come at equal interval. Then what the waiting time would be the average of the area that you see here. But in reality, it might maybe be something more like this, that there are bigger gaps, and sometimes they come together in clusters, and the area will be larger. So if you don't feel this is completely intuitive, then there is a neat kind of geometric construction you can do, that if you take this equal interval case, then number one, and then you shift this breaking point in between if you shift it a little bit, then you get these outlined triangles in number two. And if you swap them around, then you'll see that there will always be this kind of superfluous white area, which kind of means that if you do anything else than an equal separation of the inter-arrival times, then you will get a bigger area than the equal arrival time case. So the reason the waiting time paradox is a bit important is that there are many data sets, temporal data sets, they show something called burstiness. So burstiness essentially means that our activity is usually grouped into very kind of intense periods, and then have a kind of big empty idle times. A good example is if you make a timeline of the outgoing messages in your email or in your any kind of messenger, you will see this phenomenon. Now, this is from work we did about prostitution, studying online reviews by sex buyers of high-end prostitutes or escorts. It's a big data set. Here I show two kind of like on the active side, one escort and one sex buyer, and like their kind of individual activities in the data. So each line means like one customer bought sex, from someone else, and the lines that they are crossing between them is between these two individuals. The other ones goes to other people in the data, and you can see the big gaps and the cluster. I guess the sex barrier in the beginning, it's maybe not the actual time of the activity, but still, like disregarding that, there is a burstiness both in the individual activities and the kind of interaction between these two. And burstiness is known to slow down spreading phenomena like disease spreading or information spreading, or diffusion. I mean, this is a bit of a, is the physicist in me kind of shines through, because physicists call what we call diffusion cannot kind of increase in mass. So that's why I prefer spreading. But of course, in most of social science, also actually in computer science, it's called diffusion. So actually, I should change my vocabulary. But yeah, so this plot is from one of many papers pointing this out, and the m is a parameter that the larger it is, the more bursty is the kind of interevent time, and then they have some spreading, and the number of infected nodes are on the y-axis, and you can see that the oh, sorry, it's maybe the, yeah, okay, so burstiness slows down spreading, yeah. So large M I think is for memory, so it's related to that the like Markovian processes have like no memory, but you can, yeah. So it's in the terminology of the time series analysis literature. Okay, so now so now I gave some kind of overview of different studies involving time and different ways of thinking about it. I'm now kind of closing in on my own research, and you can think about temporal network in many ways, but the way I usually think about it or present it is as like human proximity networks. So who is close to whom at what time? So in this cartoon, we see a girl going around in her everyday life, meeting different people at different time, which highlights these two aspects. There's a binary interaction, that's the network, and there is the time, temporal interaction. And yeah, there could be like structure or irregularities in both the network and time, which can help us understanding the social system and things spreading on the social system. So here's a visualization of a temporal network of school kids in a French school. This is from the sociopatterns data. So I did the visualization, but not the original experiment, but it's done by putting RFID tags on school kids, primary school kids. So registering when they are within like face-to-face interaction, like 1.5 meter. And each blob here is one class. And let's see, the squares are the teachers, and the size of the nodes is proportional to their recent activity. And you will see that even though there's no information about space here, from this visualization, we can tell the story of the school day. So far they have been in their individual classrooms, and now, I guess, let's see, maybe we can kind of fast forward a little bit. So after a while, they kind of go out to have lunch. I think this is in France, so it should be pretty late. Oh, yeah, it's somewhere around here. So here, this school, as far as I understand, they have lunch in a separate building, and they go to that building together. It's a small school. I might be wrong though, so I have to double check it sometime. But at least this is a story that is compatible with what we see. So if the entire school goes together and then they split up into two like rooms to have lunch. This is what I think happens. So we see kids are mixing together, and then they within two groups, and now they go back to their classrooms, and you will see them splitting up eventually into different classrooms. Yeah, so I realized this might be on YouTube later, and I'm thinking maybe it will be watched by Alain Barra or some colleague working on this. In that case, like, please send me an email so I can correct my story. But anyway, for you, one message is that just from, you can see, kind of appreciate just the complexity that there is in this type of temporal network data sets, and also that you can use them. There's a lot of information that you can squeeze out of it, should be. Now you can see they go back to the classrooms. Okay, but that's not how the data look when it arrives to me in my computer. It actually comes in a format that is very nice for computers to read, not for humans to understand things, namely in this list of when things happen. So one line in this column, in this representation of temporal network, it tells you like who is in contact with whom at what time. But that's not very nice. Like the first thing you would do if you get the data set is that you should visualize it in some way. And of course, you can make a kind of film clip, but that's not so good to kind of reason about what's going on, because you kind of want to have all the information there at once. So instead, one typical way of visualizing temporal networks is to make these timelines of where one line represents a person, and then the contact between the person are these connections, the vertical connections. And I mean, this is good in the sense that it can convey some temporal structure. You can see the burstiness, the gaps in the activity, and so on. But you can't see the network structure. So of course you could kind of project out time and make a network of all the links that ever happen, but then you lose the sense of when things happen and the structure in time. So this is a bit of a dilemma. It's still, I would say, kind of open research question how to make a compromise. But it is a bit problematic for temporal network researchers, because one of the absolutely best things with regular static graphs is that they are very intuitive. You can like draw a graph, show it to anyone, and discuss how things spread on it, and it's a great kind of conceptual tool. But for temporal networks, that's not the case. Of course, there should be some kind of compromise. Maybe there's not the best solution, but there is definitely open research topics there, how to visualize temporal networks. So yeah, how did I get into this in the first place? So when I was a PhD student, one thing that was very popular was to measure degree distributions, and there was a hypothesis that many degree distributions follow the power law. Whether that's kind of even interesting nowadays, I don't know. But one of my ideas was that because this data set that people studied and measured the degree distribution of, they were accumulated over a long time, then many of the social network data sets, they will contain kind of links that are dead, that are not active anymore. And if we somehow can filter them out and just make a network of ongoing active contacts, then maybe we will get a more straight line, and that turned out to be the case. So this early paper, it comes up with a kind of a method to use the interevent times distributions to judge if the the links between two people is is the first observation of that link is really the beginning of a relationship, or the beginning of kind of a recurring relationship, or it's just a kind of one point in the middle of this measurement. So this paper argues that if you have like sufficiently, and the criterion is given there, if you have a sufficiently long data set, then you don't make a lot of much mistake by saying that the first observed contact is the beginning of a relationship and the last one is the end of it. And then you can take any time in the middle, the network of active links at that time is the ones that have happened before and will happen in the future. Okay, so this is how I got into it. Maybe it's not really temporal networks at the time. So, sorry, I was blanking a bit because I thought another slide would come. Here I want to say that actually one thing you can learn, and it's true for all my studies of temporal networks, is that it's a very different thing from regular static networks. It's really a different beast. You can see it in many ways. I think even fundamentally, mathematically, they have a different structure algebraically. So, for example, being connected at a distance, which is really the kind of like core for network science, that things, information, everything can flow through intermediate nodes. So being connected at a distance is not transitive property, meaning that in this case, you can go from A to B, you can go from B to D, but you cannot go from A to D without kind of going backward in time. And things cannot do that, like spreading phenomena. So, I mean, you can reach from A to B by time 11, then all the contacts between B and D already happen. You could continue to C, but you get there at time 17, and then all the contacts between C and D already happen. So being connected at a distance means something else in a temporal network than a static network. And this, there are, I mean, this including other effects have an importance for studying spreading phenomena. So the first paper where we studied like disease spreading on temporal networks was using this prostitution data I mentioned before. The prostitution paper that came out in 2010, it's more about the kind of economics and the feedback between the reviews of the sex buyers and the escort's future success and those things. But in a follow-up paper, we studied disease spreading. So this is assuming the worst case scenario of a disease spreading with like 100% transmission rate and never recovering, so the SI model. So to study the effects of time in the order of time, we took this original data set and shuffled the timestamps and kept everything else the same. So we destroyed the order of events, but we kept everything else the same, and we found that the disease in that case spreads slower, meaning that there is something in the original data that actually speeds up the disease spreading. And actually, the effect is not so big in this particular example, but you could, in follow-up papers, in later papers, I found that it can be kind of arbitrarily big. So this is a paper where we compare disease modeling, and this is the SIR model, which in temporal networks has two parameters. There's on the x-axis is the transmission per contact transmission probability. On the y-axis is the average duration of the infection. And this is once again based on this prostitution data and done in like three type of modeling frameworks. One is using the full temporal network information. One is using this like a regular static network. but kind of trying to keep it as close to the reality as possible. And then also the traditional kind of fully mixed model where everybody can connect to everyone. And essentially the spreading is slowest in the temporal network and fastest in the fully mixed. So the difference can be very big. So that is just saying that temporal effects can be substantial. But okay, back to this first study. So we put it on the archive preprint server that at that time was mostly used by physicists. Nowadays, I think even computer scientists and maybe social scientists as well put out their papers as preprints. So the funny thing is that, so the top paper here is our paper. After this paper, just a few days later, I went to a conference, met this Finnish guy I didn't know. Now he's my colleague, but I didn't know him then, Jari Saramäki. And we started chatting, and turned out that they put out a paper and did exactly the same thing. Like not with prostitution data, but with phone call data. So they scooped us actually so they put it on this archive at June 10, and we were 4 days later. Yeah, sometimes you lose, right? But anyway, so what they found was actually the opposite. So when they randomized in the exactly same way, phone call data, the things were spreading faster, meaning that there is something in their data that slows down disease spreading. And we already saw a candidate answer, namely the burstiness. But it turns out that actually both these data are bursty, both the prostitution and the cell phone data. And the reason that there is an effect that kind of overrides the burstiness in the prostitution data, and that is a bit complicated. I won't talk about it now, but it's the fact that the individuals in that data set, they come and go, so they don't spend the whole time of that data set. Turnover is much higher, whereas in the cell phone data, everybody that is there in the beginning, they are also there in the end, and all the kind of relationships kind of last through the sampling window. So we couldn't figure out that at the moment at that conference, but we decided to write a review paper and the book. Yeah, well, it's an edited volume, and later on, I have some other review papers. There's a nice book by my colleagues Naoki Masuda and Renaud Lambiot to the right if you want to learn more about temporal networks. So as a field, it kind of matured now, I think, as kind of like subfield of network science. And people are usually interested in these three topics. So I think this is also from, the slide is from me presenting myself, and the numbers are like papers from my publication list, like where they are in this kind of thematic space. So it's like, but it revolves around this kind of questions about simplifying and coarse graining, similar to community structure, and like also like how structure affects dynamics. This if like burstiness speeds up or slows down things, and then also identifying important nodes. That could be some other topics perhaps, but I think these are the kind of like main scientific questions in the field. Yeah, let's go back a bit to this randomization techniques, because that's something that people do in static networks as well, to randomize them and compare. But you can be even more, get much more out of that in temporal networks. So this Finnish group, they didn't only shuffle the timestamp, they shuffled other things as well. And then by shuffling more and more, like keeping more and more information, you can observe like how much structure do you need to keep to reproduce the original data. So like how much structure is important. So it's a kind of feature selection or like structure selection method. The randomization, not everything is worse in temporal networks. Randomization becomes a much more powerful technique. So they were actually not the first one. So to kind of come up with this randomization. So that's one of my pride that I had an earlier paper that studied something a bit more trivial, which is called reachability. Essentially something compared to the kind of size of connected components in temporal networks. Like if you arrive at a node at a random time in the data set, like how many other nodes can you reach if you go backwards or forward in time? So this is something I also studied with using this type of different types of randomization techniques. But what I didn't do, the Finnish group did, was that they kind of did it kind of successively more and more. I just did a bunch of random things. So let's not dwell too long on the plots here. You can see I didn't have many data sets. I think nowadays I have like 400 or something like that. Okay, so let's go to another. This is also a relatively old paper, but I think it's instructive. It relates to a problem in the mathematical epidemiology literature called the vaccination problem. And yeah, first maybe a recap of network epidemiology. This is, of course, totally not needed. After COVID, everybody was very much instructed in this. But just because I have a nice cartoons, then network like theoretical epidemiology divides people into different classes with respect to the disease. They could be susceptible or infectious. And then they have transition rules between these classes. So when susceptible meets infectious with some probability or rate, susceptible can become infectious, and then infectious can become susceptible or recovered, which kind of defines the two canonical compartmental models, the SAS and the SIR model. You all know this, I think, but maybe you didn't think about that you also have to connect this compartmental models to a model of how people meet, and that's where temporal networks can be useful. I guess I already mentioned this, but now the slides were here, so let's talk them through. Okay, back to the vaccination problem. So mathematically, we can formulate it like this: that how can we optimally choose a fraction f of a population to vaccinate using only local information? So assume we cannot really assume that we know the entire population and all of their connections. But we can maybe assume that we can kind of call someone up, like contact tracing, and ask, like, who did you meet? But even so, a lot of these words are a bit ill-defined. Like optimally, you can think of optimal in different ways. Is it some type of excess mortality or some economical measure? Daily is this global health community's favorite disease, disability adjusted life years, I think. Anyway, like vaccinate, like what does it actually mean? Like mathematicians, and me included, just to keep things simple, used to assume that vaccines are kind of instantly effective and like 100%, which is of course not true. And local information is also a bit, it depends on a lot of things, like what kind of disease are spreading. Of course, like sexually transmitted diseases are easier in the sense people would kind of remember their contacts and so on. But okay, in our work, we just assume that optimally means that to reduce the final outbreak size as much as possible, the vaccines are 100% effective, and local information means that you know the contacts you have experienced, but nothing else. So there was an elegant solution by Cohen, Havlin, and Ben Abraham in 2002 for the static network case. It's called neighborhood vaccination, and it goes like this: that you pick people at random, you ask these people to name a friend, and then you vaccinate the friend. You don't vaccinate the person you ask at random. And the reason this is good is that by picking a friend, you are twice as likely to pick someone that has twice as many friends. So they sample people in proportion to their friends. And of course, like people that have more friends, they also have a higher chance of getting the disease, and they have a higher expected numbers of others to spread the disease too. So in this study, we tried to do some kind of versions of neighborhood vaccination that could potentially exploit the temporal structure as well. So a nice thing about temporal networks is that you don't have to assume that the past predicts the future, which is a very unrealistic thing that you would have to do with static networks. So we took a lot the data sets we had at the time, not so many, I think 4 also, and broke them in 2. So the half time, like everything happens, we vaccinate the people and we choose which ones to vaccinate, and they also get immune, and also we start the disease at the middle point. The first half we just used to learn about the data. So here's an example without any vaccination. So in this case, the disease starts at this half time and spreads to everyone. Then we tried a few different versions of this neighborhood vaccination, and 2 of them worked better than the benchmark. The benchmark is the static neighborhood vaccination applied to this temporal network. So one is we call it the recent method, which is essentially to call people at random and ask who was your most recent contact. So this has a kind of chance of picking people who are currently in a burst, if you assume that there is a burst dynamics. And in this case, it saves one person except the vaccinated herself to get infected. The other one that worked well was called wait. So this is taking like calling people at random and ask who was your most frequent contact throughout this experience period. And then in this case, it saved 3 other persons to vaccinate them. And this is the kind of success plot. So yeah, we had 4 data sets at that time: the prostitution data again, and internet dating, which maybe not super relevant because it was more like a chatting community, something that doesn't exist today. Anyway, hospital, like who is at the same ward as someone else in a hospital, which is kind of relevant, maybe the best data set in that sense. And the final data set is an email data set. And what we see here on the x-axis is the fraction of infected people. On the y-axis is the relative performance using an SIR model compared to the neighborhood vaccination. So -20 means that we are doing 20% better. And you can see for all values of F, we can beat the benchmark. We are in the gray area. But 3 of the data set behaves differently. So the first, prostitution, internet dating, and hospital data, the recent method works better. And for the email data, this wait method works better. Which once again has to do with the fact that this first ABC data set, they have a turnover of people. So the hospital data, we had the data for, I think it was like 3 years, and people on average spend just a few days in the hospital. Prostitution data is for 6 years, and so on. But the email data is much shorter, and the people that are there in the beginning are there at the end as well. But at least we can see that there is structure in the time that can be exploited for vaccination. So I'm getting closer to the end. Just wanted to share some other, this is more ongoing work, or it's more actually not really ongoing. It was ongoing, but then some collaborators left, and now I don't really know what to do with this. But if you're interested, you can hit me up and maybe we could collaborate to finish this. But this is now again about the R0, which I think you know from the COVID. It's the number of secondary infections, like one seed node in an uninfected population would infect. So it tells you something about the very beginning of an epidemic outbreak. And then omega here is the final outbreak size in an SIR model simulation. So the idea here is that the network structure kind of creates the R0, and the R0 can predict this omega, but it doesn't predict it perfectly. So here we can see the R0 on the right, on the x-axis, omega on the y-axis for a lot of different empirical data sets. So nowadays we have a lot more data set. That's one thing you can learn from this plot. Another thing is that the R0 actually do predict omega pretty well, but not perfectly. So in this study, we want to take this kind of like a no-brain approach to measure just every single temporal network structure that we can think of, throw it into some feature selection, machine learning type of algorithm, and see what comes out of it. So ask first what predicts R0, and then what predicts the deviation between R0 and omega. So here, this is the kind of like list of all the different temporal network features that we measure. I don't even write them out, but it could be something like the average duration of a node, or the variance of the degree distribution, the skewness of degree distribution, inter-event time distribution, things like this. So we measure many things, and then we use elastic net feature selection and find out that only a few of these quantities are actually important when it comes to explaining R0 and the deviation between omega and R0. And so this figure in the middle is like a legend that you can keep in mind if you have a good mind. To the next slide, where I show where each cell in this plot shows the important features at that particular place in the parameter space of the SIR model. So we have, once again, infection probability on the x-axis and the 1 over the recovery rate on the y-axis. So the disease spreads most easily in the top right corner. And we can see some interesting pattern of the features that are important in these different parts of the parameter space. And if you look at which ones that are most frequent in this plot, it's kind of intuitive that the number of contacts, so this is what predicts the R0. Number of contacts is important, and the coefficient of the variation of the kind of full network degree distribution. Yeah. So these are important to explain R0. It's kind of in line with what people believed before in the literature. If you look at the deviation, there are, on the other hand, there are quantities related to the turnover of nodes. The average node duration is the standard deviation of that. So essentially, the kind of first order of prediction, the kind of how active the nodes are is important, and then the higher order corrections to that comes from the more temporal related quantities. And I'm almost done. I just wanted to say some other things that we wonder about temporal networks, other stuff. Yeah, one thing, this is something I want to share, from the experience of 15 years studying temporal networks, is that it really becomes so different. It's not like you can take your favorite quantity from static networks and then just generalize them. It's usually never straightforward. First of all, everything becomes time dependent, and how can you get rid of time if you want to do that, which you usually do? Do you take average? Do you take maximum? Blah, blah, blah. And if you think about community structure, it's even worse. So what does a community in temporal network even means? You can imagine if you have the proximity data of everyone on the Earth, we would find this regular IAS computational social science roundtable, that could be like one community. But then is this week connected to next week? Is it, or is it kind of split? I mean, clearly, like a community just means a different thing. And this ship of thesis story is also kind of showing that thing. So imagine now we are about 10 people in a room. It's a temporal community. Then someone leaves, maybe not me, but and then another one comes in, and then eventually everybody is replaced. Then is it the same community as we started with, or not? Okay. And then, yeah, this is a field, like, of course, it's an interdisciplinary field. So people kind of come up with similar ideas over and over. But temporal networks or dynamic graphs or time-varying networks, it's extreme. Like, and it's very unfortunate because people use different words for the same thing and the same word for different things. And every single paper you have to read, you have to start by like looking what do they really mean by this, the words they say. So that's a bit of a frustrating whining from my side. And with that, I'm done. So thank you for your attention.